When you turn the key or press the start button in a modern car, you expect something to happen. In a gas-powered car, that means the rumble of pistons and the smell of fuel. In an electric car, it's almost silent, just a smooth, instant push forward. That effortless motion comes from one of the most brilliant inventions in history, the electric motor. It may seem simple, but inside is the force that's transforming the entire automotive industry. At its core, an electric motor is a machine that converts electrical energy into mechanical motion. The principle is based on the fact that an electric current passing through a conductor in a magnetic field experiences a force that makes it move. This phenomenon, described in the early 19th century by Michael Faraday, is happening millions of times per second in the precisely engineered windings and magnetic fields of modern motors. Faraday's first demonstration in 1821 was primitive, just a wire, a magnet, and a battery, but it proved electricity could directly create rotation. 100 years later, motors were already powering trams, trains, and early experimental cars. Gasoline engines must turn chemical energy into heat, and then into motion through a complex chain of processes. An electric motor is much more direct. Electricity flows into the motor, creates a magnetic field. That field interacts with another magnetic field, and the result is torque, instantly. And torque is the secret weapon of electric cars. While a gasoline engine needs to rev up to deliver full power, an electric motor has maximum torque from the very first rotation. That's why the Tesla Model S Plaid can go from 0 to 100 km/h in about 2.1 seconds in independent tests, with no gear shifts, no turbochargers, and no explosions of fuel. Modern EVs use several types of motors. Asynchronous, or induction motors, use alternating current to create a rotating magnetic field in the stator. The rotor tries to catch up, but always lags slightly behind, hence the name asynchronous. They're cheap, durable, and extremely long-lasting. Synchronous motors with permanent magnets have the magnets built into the rotor, allowing for precise control and higher efficiency, but require rare earth metals like neodymium. Some automakers, including Tesla, mix both types, using an induction motor on one axle and a permanent magnet motor on the other, to get the best balance of power and efficiency. Cooling is a serious matter in high-performance EV motors. Small household motors can be cooled by air, but a motor producing hundreds of kilowatts in a car needs advanced cooling systems. Most use liquid cooling, circulating coolant through channels in the stator or even directly over the windings. This keeps temperatures in check to protect the insulation and prevent the magnets from losing strength. One of the most fascinating abilities of an EV motor is regeneration. When you lift off the accelerator or press the brake, the motor turns into a generator. Instead of consuming electricity, it produces it, using the car's momentum to turn the rotor and send energy back to the battery. This not only extends driving range, but also reduces wear on the mechanical brakes, since the motor itself is slowing the car down. Compared to a gasoline engine, an electric motor has far fewer moving parts. No pistons, no valves, no timing chains, no exhaust system. Many EVs use just a single-speed gearbox, transferring power directly to the wheels. This reduces losses, improves reliability, and makes throttle response almost instantaneous. There are exceptions. The Porsche Taycan uses a 2-speed transmission, but most cars keep it simple. Maintenance is minimal, often just involving coolant changes for the motor and inverter, and occasional checks of bearings. Electric motors also open new design possibilities. They're compact, and they can be placed almost anywhere in the vehicle. You can have one motor per axle or even one per wheel for ultimate control of torque distribution. Some rare production cars, like the Lightyear Zero, use in-wheel motors to deliver power directly at each wheel without any mechanical drive shafts. This allows for incredible traction control and vehicle handling. The performance of electric motors is tied to advances in power electronics. Modern inverters can switch power from the battery to the motor with incredible precision, shaping how the motor responds to your inputs. In sport mode, the motor can react aggressively for instant acceleration. In eco mode, it can be tuned for maximum efficiency. Future developments point to even more compact and powerful motors. Axial flux motors, for example, can be smaller and lighter than traditional designs while delivering equal or greater power. Automakers are experimenting with new magnet materials to reduce dependence on rare earth metals and to improve high-temperature performance. While gasoline engines will be around for a while, the direction is clear. The electric motor is becoming the dominant force in personal transportation. It's quieter, more efficient, cheaper to operate, and delivers driving characteristics that a combustion engine simply cannot match. When you feel that smooth, instant surge in an EV, you're experiencing a piece of technology that's more than 200 years old, but still shaping the future of mobility. Subscribe us for more videos.